I'll give some opening remarks and then we'll get on with our first session. So I'll just start from why do we have this workshop and how the idea came by. At the beginning of this year, we released a grid forming technology and energy systems integration report. So this report followed up from a paper we had in IEEE Power and Energy magazine, and you can see some copies if you like to grab a copy. You can see there at the registration desk. It was a special issue on inverter-based resources that Charlie Smith, CEO of ESIG, guest edited. And so we had one article there that talks about future of inverter-based resources and kind of alludes into role of grid forming inverters in that future. And then from that paper, we followed up with the report that was developed by our high IBR task force under reliability working group at ESIG. So here at glance, you can just see an overview of the report. We talked about differences between grid forming and grid following resources. Some of you who have been in the tutorial earlier today heard some of the pieces that actually went into the report. Then we talked about system needs and what is changing with higher shares of inverter-based resources and trade-offs between system needs and resource needs. So where is it that the characteristics of the system need to meet the characteristics of inverter-based resources, or is it that inverter-based resources have to deliver all services and grid doesn't have to do anything? So there is this trade-off that the report talks about. Then we talk about system services and technical requirements and breaking so-called chicken egg problem. I'll have a slide on this slightly later today. And then global experiences with introducing interconnection requirements and services around the world. So it gives an overview of what already exists today. Then there is a chapter on advanced characterization and testing of grid forming resources. And it walks through tests that are applicable to both grid following and grid forming inverters. And then the tests that would be specifically needed to verify grid forming capabilities. And then talks about some of the field tests, which are not real tests, but that are things that happened to grid forming projects that already exist in the world. And then one of the last chapters is on tools. So it's talking about needs to further develop tools for simulations of systems with large shares of inverter-based resources and grid forming inverters specifically as well. And talks about stability tools, analytical tools, economics tools, and how these tools now need to be integrated more closer together to pass results from one tool as an input to others. And then some conclusions and recommendations. And so in my opening remarks, I'll have a couple of background slides that are based on the report, but I will not talk about the report itself, and you can click on the link. It's actually linked here in the thumbnail, and feel free to review the report. It's a good read. So just to set the stage where we are today, this chart is showing it's from NREL, and it's showing penetration levels that have been reached in different areas. And when I'm saying penetration level, in circles here, you can see instantaneous percentage of load that's been served by inverter-based resources in this different size of systems. And then what you can see in circles, you see energy that's been served by inverter-based resources annually. And then in squares, you can see instantaneous percentage. So instantaneous percent of load that have been served by inverter-based resources. And so on the left-hand side here, you can see that some of the systems are already reaching 100% instantaneous penetration of inverter-based resources. And these are small island systems. And as you get to slightly larger island grids, and even Ireland is included as one of the larger island grids, then the penetration levels in terms of energy are getting lower, but still you are in a really high percent at some instances in time. And so you serve quite a big share of load from inverter-based resources already. And actually Ireland now went to 75% penetration levels maybe early this year. And then there are even larger systems and large interconnected systems that are, not yet there. So you can see here, Western Interconnect is one of the examples, and ERCOT system is a Texas system, which is a bit in between. So it's a large island system. It's also reaching 66% penetration, instantaneous penetration levels already. As you heard in the tutorial in this morning, the majority of inverters today are grid following. They read voltage and frequency of the grid, they lock onto that and inject power aligned with the signal. The signal currently comes from synchronous generators, and as you get more and more of inverter-based resources and further away from synchronous generation, the grid conditions get weaker, and signal is then easily perturbed by injection of inverter-based resources themselves, and it makes hard for inverters to lock on to the signal correctly. This may lead to local instability issues, and this is why we are talking about grid-forming inverters, maybe to provide stability. So what you can see on the left-hand side of this slide here is a schematic chart, and we have in the report. So everything above the blue line kind of represents stable behavior, and everything below blue line is unstable behavior. On the x-axis, you can see percentage of inverter-based resource penetration as a portion of instantaneous load. And also at the same time, you can see some kind of equivalent short circuit ratio characterization. So this is characterization of system strengths. And so initially, as we started getting inverter-based resources on power grids, basically the idea was just to get out of the way, and if there is a disturbance happening, you can just trip offline, and that's all you need to do. Gradually, as we're starting to get more percent of inverter-based resources on the grid, started requiring grid-friendly capabilities from inverter-based resources and ask them to ride through faults. As we get into higher penetration levels and weaker grids, then we ask for advanced controls from grid following inverters so that they can operate stably in lower system strength conditions. And we're looking for some ways to mitigate control interactions in areas that are high on inverter-based resources. As you get even further at higher penetration levels, above probably like 50% or more, then you need further control advances. People starting to look at synchronous condensers to provide stabilization. But as we push system even further, then we start talking about, so what if inverters themselves provide this stabilizing quality? And that's where we get into talking about grid forming inverters. So in the report there, we developed a high-level definition of grid forming inverters. I brought it up here. I kind of will read it through just for the benefit of setting us all at the same on the same page. So the primary objective of grid forming controls for inverter-based resources is to maintain internal voltage phasor. When grid forming controls are applied in transmission connected inverter-based resources, the voltage phasor is held constant in transient and sub-transient timeframes. This allows inverter-based resources to immediately respond to changes in external system and provide stability and controls during challenging system conditions. This phasor must be controlled to maintain synchronism with other devices and control active and reactive currents to support the grid. When grid forming controls are applied in non-transmission connected inverter-based resources, for example, for black start or in microgrid applications, this synchronization functionality is removed or limited, and the voltage phasor may be held relatively constant over time, and the plant operates in electrical island and defines its frequency. There are many variations of grid forming and grid following converter controls, and both are subject to physical equipment limitations, including voltage, current, and energy limits, and also mechanical equipment constraints, for example, in wind turbine generators, and also external system limits. I mentioned chicken egg problem when I talked about our grid forming report. I think from the discussion that happened during the tutorial, we're still there. We're kind of in this chicken egg situation where grid operators find it challenging to require functionalities from inverter-based resources that are not widely available. Inverter-based resource developers will normally go for features in the inverters that are incentivized or required. And so in the absence of this new advanced features from inverter-based resources, the system operator goes with limiting output from inverter-based resources or limiting where inverter-based resources can be built. As a result, developers will find it increasingly difficult to develop new inverter-based resources. Manufacturers may see shrinking markets for inverter-based resources, and all along manufacturers are just, asking, what is it that system needs and what are the capabilities that we need to deliver? And so the question is, which comes first, capability itself or requirement for capability? How do grid operators know what performance or capability is possible from new equipment and what they can conceivably require? How they can go about evaluating the costs and benefits for having such equipment on the grid, and therefore introducing incentives and markets for the services, and what drives manufacturers to invest in new technology without having any incentives. So we tried to look into this chicken egg situation in the report and came up with a workflow that I'll be talking about next. But as we alluded to during the tutorial, the failure to find an exit from this chicken egg problem could hinder our ability to meet our environmental goals. And as Andrew mentioned, around the world, there are thousands of megawatts of inverter-based resources in the interconnection queues, and specifically batteries. And all of those so far are being planned as conventional grid following technology because there is no incentive or clear guidelines as to what grid forming inverters are supposed to do, or if we even need grid forming inverters. And so resources in the absence of this clear requirements, they will be built as grid following technology, and this increases system needs for grid forming or some kind of other stabilization equipment in the future. And so Deepak showed this example in the tutorial in more detail, but here I just have an illustrative example where you have a grid with 3 grid following resources, and you have an external grid, and then if external grid disconnects, then this island cannot operate stably with these 3 grid following resources. So to provide stabilization and to let this island operate stable when the external grid disconnects, what you can do is add grid forming inverter-based resource to improve stability. And so that would be an additional asset that you need to invest in and connect it to the grid to provide stabilization to already existing resources. But what you could have done instead is that if this one of these resources would have been built as a grid forming to start off with, then you don't need this additional equipment to provide stabilization. You can get away with just these 3 resources and have a stable island just with that. So we developed this kind of schematic workflow that system operators may use as they think about incentivizing I don't even want to say grid forming services, but services, new services that system needs if the system experiences high shares of inverter-based resources. So the starting point is a target system that the system operator needs to define, and I think it comes from environmental goals. So basically, what are you trying to achieve? Are you trying to achieve 100% inverter-based? Are you trying to achieve 100% carbon-free system? How does this system looks like in terms of generation mix? And then the next step is to define resilience parameters. So kind of what are resilience parameters you're trying to achieve? How much load shed you can live with? How often you can allow load shed to happen? What are the costs of that? So you define kind of what are the edges that you can push system to. And then perform studies to determine in these conditions, what our system needs. And based on that, you formulate technical requirements for system services. You quantify how much services you need for the system, and that probably will be specific based on system conditions. So it will not be flat amount of services throughout the year, but probably it's at different system conditions, you need different amounts of different services. Then you look at this and you define, can you economically procure it through market, or is it, a requirement that needs to be applied to all resources on the grid? So you figure out a way to procure the services either through markets or through requirements. You define technical benchmarking. So how are you going to evaluate that resources are actually providing these services? You implement services, so you kind of set this all up either through interconnection requirements or market rules. And as you start getting contribution for the services, then you monitor performance. And so once you have this established, then equipment manufacturers can develop and test required capabilities for resources to provide services. Developers will evaluate and build required resources that can provide required system services. And they'll have clear guidelines as to what is expected performance and what are they expected to get in revenue from providing the services. And then developers will undergo testing and qualification to provide the services. So, I mean, it sounds simple. It's not as simple as it sounds, but it will take steps. But we feel like it starts from a system operator to define what our system needs and work from system needs perspective. And I think that was Deepak's message too in the tutorial. We shouldn't prescribe what technology is supposed to do. We should prescribe what system needs are, how much you need of each of the services, and let equipment that is capable to deliver it economically come and deliver. I have this list of pilot projects, and again, Deepak mentioned some of this in the tutorial. So I'll just quickly run through it. There is a handful of pilot projects around the world where grid forming is already being used. So the first one is from GE, where grid forming inverters in batteries were used to black start gas-fired turbines, and then gas-fired turbines were used as black start units for the system. And then there is a grid forming battery set of batteries by SMA in island of St. Eustatius, and that allows 100% inverter-based resource application. So island can operate with 100% of inverter-based resources at times and not use diesel. There's a wind farm in Scotland. This is where over a period of time, wind turbines that were initially built grid following were converted into grid forming. So the controls were changed. So they operate in grid forming mode, and they operated like this in grid connected mode initially for a period of time and experienced and responded to faults that were happening on the grid. And then they also tested island operation and even black start operation, where they black started that wind farm itself with a local load and energized all the way up to transmission transformer. And then Dalrymple battery storage. This is where a battery storage, grid forming battery storage can operate an island grid on the end of the long feeder in Australian grid. So when it's grid connected, then the battery storage operates as usual. When it gets disconnected from the grid, then the grid forming battery storage forms that island and supports island operation. Hornsdale battery storage project in South Australia. It's 150 megawatt battery storage project. Initially was built as grid following, but currently is undergoing conversion of inverters to grid forming mode. And Deepak also had the slide during tutorial. Actually during this conversion exercise, a coal-fired plant tripped offline in nearby, and they were able to record the difference between how the entire plant responded to that generator trip, which looks like a primary frequency response, similar to how the synchronous generator would have responded. But if you look at just those inverters that were already in grid forming mode, you can see a response that's similar to inertial response of a synchronous generator, because they the control mode that they implemented there is virtual synchronous machine mode. Then there is a number of grid forming projects that are underway in Australia being developed right now. I have a stability pathfinder listed here from Great Britain. You'll hear more about it during the workshop, but this is, we see it as one of the ways to kind of follow this workflow that we've developed. We actually developed this workflow and then we looked at Great Britain and saw that they are actually already implementing that. So they have this stability pathfinder is an incentive to procure services that are disappearing from the system as synchronous generators are retiring. So they're looking currently to procure additional amount of system strengths, and they express it as amount of short circuit current that they're looking for in certain locations on the grid, and a certain amount of inertia in gigawatt seconds. So they determine it as energy injection in inertial time frame. And so through the stability pathfinder, the first phase was just for synchronous machines for existing technology, whereas second and third stage are open to any technology. And the second stage just concluded, and they procured 5 grid forming batteries as a result of this tender. So 5 resources are synchronous condensers and 5 are grid forming batteries. So this is an excellent way to incentivize grid forming capability through definition of through clearly defined services. And then Great Britain is actually the first one to develop interconnection requirements for grid forming capability. And this is non-mandatory requirement, but it's a grid code requirement that describes in some detail as to what is expected from a grid forming resource. And again, to the point that was raised during tutorial, they don't prescribe what kind of controls resource should have, but rather what kind of performance is expected. Okay, so moving on to the workshop, we have a pretty interesting agenda. We try to organize agenda around this workflow that I've shown, but then actually because of availability of presenters, we had to move stuff around a little bit. So it doesn't quite follow this, but you'll see the themes are the same as what we have in this workflow of deploying stabilization services, new services on the grid. So the first session is on defining technical requirements and qualification of services. And then the second session is on defining target system and desired performance and system needs studies. And here we'll have a showcase from Australia. So we have the entire session from Australian system operator. And then in the evening today, we have a networking event. So I invite you all to go to the 3rd floor and network. Then on Wednesday, we'll start with talking about grid forming capabilities and challenges. The next session will be about incentivizing new grid services, performance monitoring and grid forming pilots and projects around the world. So you'll hear about some of the projects that I mentioned on that list. And then session 6 is on performance benchmarking, modeling and testing. And then on Thursday, the first session will be on research roadmaps. So you'll hear about what research community is up to with regard to grid forming inverters. And then we'll have a closing panel, which will be no presentations, and we'll just have an open discussion about what's next with grid forming inverters. So I would like to welcome you all, and I have a list of virtual and real visitors, and thanks to all who came in person. We have a number of countries, an independent state of Texas, that's what Charlie likes to put on slides, and I have it too. I'm from there. So take your time making your friends, and we're looking forward to another great meeting. Before I conclude, I actually wanted to talk about what are next steps for ESIG. With regard to grid forming inverters, as I mentioned, the grid forming report came out of the high penetration of inverter-based resources task force. So this year we would like to continue looking at services. So we looked at technology and kind of what's out there, what is the landscape, and the next step is to approach it from a different end and look at system needs and services. So we are planning to review requirements and specifications that already exist for grid forming capabilities. So looking at GB requirements, there is a number of other initiatives out there to review. And then we'll start from a system needs and services report that was produced by Global Power System Transformation Consortium. And I'll mention what it is on the next slide. And so that report looked at what a system needs, and we'll use it as a starting point and try to convert it into high-level definitions of system services. We'll use a small test system to define services, but also to test what is how grid forming resources can provide these services. And then the report can serve as a guide to system operators who are just starting on this path and considering developing requirements for services or requirements for grid forming capability. So I mentioned Global Power System Transformation Consortium. I'll just spend a minute here. This is a global organization bringing together researchers and industry from around the world. It has many organizations in it. The consortium consists of 5 pillars. The first pillar is on system operator research agenda and peer learning. And this is a pillar that ESIG is leading. This pillar is around, it's been created around 6 system operator needs. And so these are 6 system operators that are kind of pushing the envelope now and have high share of inverter-based resources on this system. And this is EirGrid, Great Britain system operator, ERCOT, AEMO, Danish system operator, and California. And so I'll mention what the research agenda is on the next slide, but this is the first pillar that looks at system operator needs. The second pillar is trying to bring that knowledge that this system operators already have to power systems that are next on the path of integrating higher shares of inverter-based resources. So kind of just like spreading the knowledge and experience. The third pillar is on workforce development, because we recognize that there is a need of more engineers who understand converters, and there is a need for more education. So this is what the pillar 3 concentrates on. Pillar 4 is on adoption of technology and standards. And pillar 5 is on open source tools. So it basically looks around the world and looks at tools that have been developed and are open source and tries to document it so that people can use it. So just a little bit more on pillar 1. As I mentioned, 6 system operators got together with some researchers and leaders in this industry and developed, during the course of 9 months, they developed a research agenda. And this is basically 60 questions that system operators, the 6 system operators need to solve yesterday. So they are looking for solutions. There are no solutions out there, and they are already now needing some of the solutions. So these are the 60 research questions, and they can be broadly grouped into inverter design, analytical tools, control room of the future, system planning, and black start. And so now pillar 1 is trying to create collaborations between industry and research to answer some of these research questions. And I have inverter design there. So this is where grid forming, deployment, and issues related to deployment of grid forming resources is being dealt with. And one of the initiatives that we are currently considering is also creating a technology council within the grid GPST to bring more of manufacturers of inverter-based resources to the table and kind of discuss the issues that system operators are experiencing and manufacturers are experiencing, trying to solve it and maybe solve this chicken egg problem that I was talking about. So I wanted to mention some upcoming workshops that ESIG is going to have. We will have our regular fall technical workshop in October in Minneapolis. Our spring workshop in Tucson in March, and then the next workshop, meteorology and markets workshop, is already scheduled for June 2023. So this is the workshop that is happening in parallel with this special topic grid forming workshop today. And so I would like to welcome you all to attend these workshops in the future. And with that, thank you very much and welcome to the workshop. I hope you enjoy. We won't take a break here. We'll just take a minute to switch to the next presenter and we'll continue with the session. All right, so we'll go on with session 1, and Jeff Billo, who will be chairing this session, you can start.
Okay, thank you, Julia. So I'm glad to be joining you all today. I really wish I could be there in person, and not just because it's 101 in Austin today, but also because this is such a relevant topic, and ESIG has assembled really an all-star group of experts to present. And so I'm looking forward to our session, but also the coming sessions as well. So this first session is on defining the technical requirements and qualification of services for grid forming inverters. So we're going to hear from National Grid. We're going to have a presentation on the Hawaiian experience and a presentation on Unifi. And afterwards, we'll have some time for Q&A. So today we are really fortunate to be joined by 2 experts across the pond from National Grid. As many of you are probably aware, National Grid has been one of the leaders in grid forming inverters. And so we're going to start today by hearing from Tony Johnson. Tony has been with National Grid since 1993, and he's worked in a lot of different roles there at National Grid, including in system operations. He's worked on generator compliance and dynamic modeling issues. He's worked in the development of grid code requirements, and he's been involved in the development of offshore grid code and transmission system requirements. And more recently, he's also been working on this grid forming technologies and the technical requirements. So that fits very well with what we're going to be talking about today. So, so very happy to have him. Also, his colleague, Dechao is also going to present the National Grid perspective. Dechao is a power system engineer and a subject matter expert in DC systems and power electronics at National Grid. Dechao has obtained his PhD in electrical engineering from the University of Birmingham. So with that, I'm going to turn it over to Tony first, and then Dechao will follow.
Superb. Thank you very much, Jeff, and good evening, everybody. Well, it's good evening here. I think it's good afternoon in America. So I'll just get the screen up and hopefully we'll be able to. Can everybody see that? Yeah. So.
Not yet, Tony.
Not yet. Okay, hang on. Thank you for that.
Sure.
Let's just try again.
Yep, there you are.
You got that? Okay. Good. Superb.
Thanks.
So just before I start, a lot of you will be very familiar with National Grid ESO. We are the operator of the transmission system in Great Britain, which includes England, Wales, Scotland, and the offshore transmission network as well. This is probably the accumulation of about 10 years of work on and off, you know, it's nice to see this actually come to fruition. And the other thing is also a big thanks to Julia for setting us up very nicely to talk about the issues. Unfortunately, it's not possible to try and condense 10 years of work into a short presentation, but hopefully we will cover the key elements. So this will start really by just covering. Everybody knows, and I think this has been well documented, that as we move from systems made traditionally up of synchronous generation, a lot of which has been derived from thermal plant, coal and gas, the drive towards renewable sources is resulted in obviously a different technology. And as we all know, the inverter bay, a lot of renewable plant, wind, solar, batteries are all derived from very different technologies and the synchronous counterparts. And whilst you're getting a megawatt for megawatt replacement, you might have, say, you know, just taking a simple example, 500 megawatts of conventional combined cycle gas turbine or 500 megawatts of coal-based thermal synchronous generation, that will be replaced by 500 megawatts, say, of wind power or solar power. But the thing is, because technologies are very different, you're not getting exactly the same performance requirements. And the thing is that the technical operational requirements or technical operational characteristics of a transmission system are largely dictated by the generation and demand connected to it. So as you start to see this change of plant moving from synchronous plant to asynchronous plant, you start to see some significant shift in the performance of the power system, not least under fault conditions. So we have to operate the system in a safe, secure, and economic manner, which means we design and operate our network to the security, quality, supply standards, which means we cater for double circuit faults amongst loss of generation up to a certain size. As we start to transition to that move from synchronous plant to asynchronous plant, we start to find that faults that we were secure for, we're no longer secured for, and we need to get to the bottom of that. So the prime aim here is to operate a safe, secure, and economic system using low carbon sources. And how do we overcome that dilemma? So the first thing we need to look at is what's actually going on here under a fault condition, and what is a synchronous plant giving us that an asynchronous plant or a grid following converter wouldn't be, and then ask the question, well, how do we address that gap? So the first thing really here is to understand what synchronous generators are doing, and then what are grid following converters doing, and how do we plug that gap? So as shown here, a synchronous generator, obviously they're frequency and phase sensitive, so they respond instantaneously to system phase changes. The other thing is synchronous plant, and I know a lot of you will be very familiar with this. They supply significant fault current injection, typically 2 to 4 per unit at the connection point, even 5 to 7 times at the terminals, where you're not going to get anything like that with the traditional converter-based plant, because the fault current's limited by the insulated gate bipolar transistors and the semiconductor devices controlling it. The other thing you got to remember is that with synchronous plant, there is generally a large rotating inertia, which through a turbine, and then the actual rotor of the machine, which obviously is directly coupled through the electrical winding to the system. So there's direct coupling, and that stored energy in the rotating mass of the system is transferred as energy into the system. And again, because you often get a lot of converter-based plants, which, particularly for things like batteries, which generated at DC and then reconverted to AC, you don't get that inherent electromechanical linkage that you do with synchronous plants. So that lacks your inertia. And then, whilst traditional converter technologies provide fast fault current injection, they're often based on a measurement and a calculation resulting in a delayed response. So the thing about a lot of converter-based plants, they use phase lock loop control or similar technology. What that does is measures the phase angle of the AC grid's voltages to rapidly change the phase angle of the inverter internal voltage source, to stop changes in the inverter current by keeping the angle across the internal voltage and the terminal voltage constant during AC power transients, and that can cause some serious problems. So the one thing to remember here is that the key point that we're trying to derive here is how do we get a converter-based plant to behave in a similar way to a synchronous machine. And if you look at the top graph, this is just showing synchronous generator fault applied to synchronous, a system comprising only of synchronous plant. And the thing is, you get an instantaneous rise in active power, which is basically the phase jump power. As soon as you get a disturbance on the grid close to the machine, there's an instantaneous phase change between the terminal voltage, between the voltage seen at the connection point and with respect to the internal voltage source, and that phase shift causes an instantaneous power jump. And that's very, very important, because under the area under that curve is additional active power injected into the network, which you don't get with grid following converters. Now, we did a number of studies going back some time, and if you do nothing, actually a grid following converter will actually do nothing. And then you can apply some various control functions to that. We did some modeling in an analysis program called Dig Silent Power Factory, where we've got a static converter with grid forming, which is shown by the red curve, and you can see you get a pretty much a pretty fast rise in response. So that's resulting in the grid forming capability. And the thing to remember is, with phase lock loop, the problems is that you get a fault or a disturbance. There's a calculation. The plant responds, and then it does a response sometime shortly after that. But the plant isn't actually operating in synchronism with other machines, so you don't get that collective push that's helping to stabilize the system. The subsequent graphs there, the purple, we've got a static a converter with a phase lock loop with 2 different control settings. And a slightly lower rating. And in this case, we managed to get a fairly good performance, but it's not as good as the grid forming. And then we just had again a slug static generator with a fast fault current injection requirement, which was quite slow. But the important point here is that what we're trying to mimic is the fact that we're trying to get for that phase change, you get that instantaneous inherent performance, instantaneous injection of power into the system, which is so vitally important. Getting that power in, so all the plants working at the same time, and it's absolutely mimicking the same performance that you get from a synchronous plant, is very, very important in stabilizing the grid. And we'll come on to the fact later that it's important both from a regional level and a national level as well. So how all this came about? Well, within GB, we've got a grid code, and the grid code process is managed through its own governance arrangements. And the aim of the 137 work group was to get industry experts together and then develop a grid forming specification based on the minimum needs of the transmission system. So its aim was to develop a high-level flexible specification. This would be non-mandatory, and it would be necessary to provide necessary framework so the specification could be used for future market. The other key point is when we did the studies looking at this probably about 10 years ago now, we identified that actually to ensure you've got a stable system, it was only when you got above about 65% non-synchronous generation did you start to run into problems. So you don't need grid forming on every plant 100% of the time. And that actually gives us a few tools to play with. So as a result of that, we could then go away and say, well, what actually do we need? So that resulted in the development of a technical specification of the plant requirements in terms of what do we want. And I've got a few slides on that in a minute to bring out the specific elements of the technical specification that we're after. And then in addition to that, how do we model this stuff? What data needs to be submitted by a developer? And then the other part of it is the actual compliance process in terms of providing a true and accurate model of the plant as built, and then going out to be able to do tests on that plant so we can verify that the data in the model submitted is a true and accurate reflection of that plant as built and constructed in that power station. As Julie has mentioned, we've also got the Stability Pathfinder work, so we were looking for consistency with that. But having said that, as this work has progressed, the Stability Pathfinder work has been developed over several stages, and we're now in a position where the latest stage of the Stability Pathfinder work is actually using the GC0137 grid forming specification that we've developed through this work. We've also established another separate expert group, and Dechao will be taking you through some of that. So the grid code defines the high-level requirements for grid forming and the specification. Some of the more detailed elements, which we got a lot of comments about from the work group, really about some of the more detailed elements. So the actual grid code itself isn't an actual formal functional specification, it's a set of high-level requirements. During the process, we got a lot of comments about how this specification should develop. So things like, can you provide some examples of work examples, simulations, testing and monitoring techniques? What's a good performance? What isn't a good performance? How does it interact with other plants on the network? So the best practice guide is looking at those sorts of things, and Dechao will be saying a little bit more about that in a few minutes. And then the other element, which is sat outside of GC137 but is very related, is the development of a longer term ongoing stability market, which would sit side by side by the Stability Pathfinder work. Whether or not actually in the longer term Stability Pathfinder and a stability market will actually be merged as one. So going forward, it's the stability market that will actually be used to develop the requirements that we want in real time. So at day ahead stage, we will identify the volume that we want and then use a market to procure that. And as I said, the 137 specifications is a formal technical specification. So the key elements, what do we really want from grid forming? Well, the first point is that the actual plant itself should comprise, and this is available firstly from any type of plant, be it a wind farm, a solar, a battery, even electric vehicles or smart loads. But the important elements that we're looking for, so we're not looking specifically at the type of plant, we're looking at the key capabilities. The first thing is the transient, basically it should have a transient impedance of the AC grid that's not provided by a phase lock loop based traditional converter. And as I've said, the reason why we wouldn't want that. And then the key criteria that we're after, I've got a slide on this in a minute, is the phase jump power. And as I've mentioned, the phase jump power is related to the instantaneous power injection that you get from a phase change. So if you recall that the power in a synchronous generator is equal to the internal voltage times the terminal voltage divided by the synchronous reactance multiplied by the sine of the load angle. As soon as you get a phase change between the terminal voltage and the internal voltage source, you'll get a power change. We also need inertia power, which is obviously the contribution as the speed of the system starts to change. You'll also get the injection of power. So we know that the rate of change of frequency is equal to 1/2h times the rate of change, but times the power difference. So we'll know that we get a power inertia or a power injection from a frequency change, which is another element that we want to achieve. And also, in addition, we will also get a small contribution from damping power. So a lot of synchronous generators are fitted with damper windings, which is effectively like a form of basically induction machine connected on the back end of the winding. As soon as the frequency changes, that induces a current to flow in the winding, which then produces a very small component of power. And when you add all of those up, these are all important power elements that are released to the system during a disturbance. And that's very important, bearing in mind that frequency and power are inherently related. When you add these up and you add them up across the network, the power that you get is important in stabilizing the grid, which you don't get from grid following converters. So we've got some characteristics here which show the behavior of some machines under a fault condition. So these are real live graphs that were taken from the system a few years ago with synchronous plant. And the top graph is just showing system frequency against time. And we've got basically there are two remote generators, units 4 and 5, with low rate of change of frequency and oscillations. But the important one I really want to focus on is the lower graph, which is bringing out all of these key elements that I talked about. So type 1 is an active phase jump power. So as I've said, as soon as you get a phase change, you'll get an active injection of active power as a result of that phase change, which we call phase jump power. Type 2 is the active inertia power. So as the frequency starts to change, you'll get an injection of active power, which is type 2. Not huge, but nonetheless is a component. And then the damping power, the effect from the damper winding, type 3, again, a smaller component, but again, when you add these up, it's still all valuable. And then what we call type 4 active control-based power is basically, that would be the active power that you would get from then the control action that you get from the governor system. So as soon as the frequency starts to change, obviously the governor valves start to open, there are time lags through their operation, and then they start to pick up. So this is basically covering your primary, what we call in GB, the primary and secondary frequency control. So basically the governor valve is opening up, and the plant is then starting to provide power to the network through the control action. But the important thing to stress is that types 1, 2 and 3 are inherent capabilities of a plant without any control action. That would be the normal capability you get from a synchronous generator under a faulted condition. And that's exactly what we're trying to mimic through the grid forming work. And this is just showing a simulation of of a fault. So for a 20-degree phase jump followed by a frequency change of 1 hertz per second. So the important thing, if you look at the, so we've got obviously the falling frequency, the phase shift, and then obviously on the bottom right hand, we've got the internal voltage source power, which is showing that pretty much instantaneous rise in active power to the disturbance, which is the type of performance we're trying to mimic. So in terms of compliance testing and simulations, so we are well versed in GB with compliance testing and simulations, and making sure that the plant as built is capable of meeting the requirements of the grid code, and the models that we get from that is a true, the model that we receive is a true and accurate reflection of the plant as built. So on the left hand side, our normal standard tests and simulations that we would need on things like reactive capability, voltage control, active power control, frequency response, fault ride through, etc. That's all bread and butter stuff we would do anyway for any type of plant, whether it's synchronous or asynchronous. Now the new element is the middle box. So we need to introduce some grid forming tests to demonstrate the capability of the plant to provide phase jump power, inertia power, and damping power. And basically when we add the two up, so that the tests and simulations that we would normally require under the grid code plus the grid forming tests, then that results in the total suite of tests and simulations that we would be required to perform on the totality of the plant. So where the important element is that grid forming is a non-mandatory requirement. It would be selected for use through obviously the stability market that I've mentioned earlier. Basically, when we actually go through a plant says, yes, I'm prepared to provide grid forming, this is the cost, then there would have to be through a set of compliance tests, and this is effectively how it would be done together with associated simulations as well. In terms of how this would all work in the real world, there's still some work to be done on this, but I've said that we've got the Stability Pathfinder, and what the Stability Pathfinder does is expressing long-term expressions of interest for parties to provide stability products over a long-term time frame. There's also shorter-term stability market, which we're looking at, and this is all still very fluid at the moment. There's still a lot of work going on this, but the important part is that the stability market is going to be used to procure what the system operator needs in real time to ensure that we can operate a safe, secure, and economic system. And in doing that, we've got the right volumes of grid forming, both at a national and regional level. And how would we do that? Well, this is all still very under development, but basically one way we consider it is that you have the basic plant schedule, which basically assumes no real constraints. It would just basically say, this is the demand on this day, this is the generation running based on its merit order and cost, and in that you might have majority might be say wind or solar, there might be 1 or 2 hydro plants, there might be 1 or 2 nuclears. The ESO at the day ahead stage would know how much grid forming capability it needs at the day ahead stage, both on a national and regional level. So it would then go to the Stability Pathfinder and say, well, I've got these providers that will meet a certain requirement. So I get some providers through the basic plant schedule, say for the hydro and the nuclears will naturally provide grid forming. The Stability Pathfinder will also provide some grid forming. Then we look at the grid forming market, which would basically say, which developers are willing to provide a grid forming capability and what's the price for them, and are they in the right place. So we would use that. And then, if you recall, I talked about the active inertia power, and then the active inertia power is derived from other markets. So we would have dynamic containment and frequency response provided through those markets. And then just to finalize,
Tony, I apologize to interrupt. Just keeping an eye on the clock here. We probably need to move on here soon. Sorry.
Yeah, I'm on the last slide now. So just for your information, the grid forming specification was approved by our regulator in January 22, and it was implemented in our grid code in February 22. The work's consistent with Stability Pathfinder. There is rafts of information from that link on the grid forming report. So that's well worth a read, but do make sure you get enough time because you need a good half day. The best practice guide is now performing, and Dechao will mention that. And then there's obviously we're working with partner organisations to develop the stability market. And we just want to say that we had over 40 people from all across the world involved in this work. And in particular, we'd like to say a big thank you to NSTOR, Siemens Gamesa Renewable Energy, and GE. So thank you for your attention. I'm sorry I've overrun, and I'll now hand it over to Dechao.
Hi everyone, greeting from Dechao in the UK. Thanks for the invitation for this event from ESIG, and following the Tony's presentation about our GC0137. Now I try to give you a brief introduction of our current grid forming development and this stage. Okay, I share screen with me. So I share the screen. Everyone can see my screen.
Yep, looks good. Thanks.
Okay, brilliant. Okay, since last summer, I have been leading National Grid ESO's further development of Great Britain grid forming best practice guide in collaboration with comprehensive external stakeholders in the GB and wider. Initially, all parties in this best practice group co-shaped and agreed our objectives and terms of reference. As Tony mentioned, GC0137 is not a detailed technical certification. So in our best practice group, we aim to use this opportunity to capture comments on GC0137 clauses from our external stakeholders and provide necessary guidance and information, filling in any understanding gap for facilitating future grid forming applications within the GB energy market. Those areas touch upon maybe about analysis method and complex testing as mentioned by Tony. Additionally, we think it's a really good opportunity to capture good practice in the GB and wider, as grid forming is still developing and is early stage with a series of technical challenges to be addressed. So we have invited quite a few external speakers from different backgrounds around the world to share their good practice or share their insights into the opportunities, challenges for the GB grid forming technological development in the GB energy markets. Finally, after consulting with comprehensive internal and external stakeholders in this best practice group, if we can co-identify the strong evidence to improve our grid code following their comments, we will capture those suggestions for further GC0137 modification after this best practice guide. A group of external subject matter experts from GB and wider have been working closely with ESO to co-address technical challenges as arranged for the following 4 subgroups. Subgroup 1 is about definition of the GB grid forming plant and its functionality, and is led by me and supported by another 14 experts from different backgrounds. The main tasks for this subgroup have been completely to provide the necessary clarifications and the information for the definitions of the GBGF plants, internal voltage sources, and the GB functionality as required in GC0137. Subgroup 2 is also led by myself and supported by another 12 experts. The main tasks for this subgroup have been nearly finished to capture all the relevant time domain methods, including the EMT and RMS and the frequency domain analysis method including the validated impedance-based method as well as some emergent methods such as the network frequency perturbation. We evaluated strengths and limitations of different methods for specific type tests of the GBGF functionality. Meanwhile, as we introduced a new method to use the NFP, for many external stakeholders, this NIP concept would be new for them. So in this way, we hope to provide more details for basic principle guidance on some tools for NIP plot production as developed and shared from some external contributors. Subgroup 3 and 4 are ongoing to identify any unique requirements for GBGF plants in terms of the modeling requirements and complex testing. If some requirements are both applicable for grid forming and grid falling converters, those requirements will be covered in GB's existing development in GC 0141 for modeling requirements and existing documented compliance testing guidance for IBRs. Because if you see Tony's slide about compliance testing, you can see the far left side about such generic compliance tests. So those subgroups 3 and 4 are expected to be completely by end of July, and the GB grid forming best practice guide is expected to be released at the end of the Q3 this year. So welcome to join our best practice group to support to us, particularly in subgroup 4 for complex testing, as some topics are very challenging. For example, the phase jump, as also mentioned by Tony. That's the end of my presentation. Thanks for listening.
Okay, thank you, Tony and Dechao. Next, we're going to hear from Andrew Isaacs, who is a Canadian, but he's going to talk to us about the Hawaiian experience. Andrew has been with Electranix since 2003. His bio mentions specializations in renewable interconnections, weak grid, and SSR and SSCI issues, as well as large-scale EMT system modeling. So to say that Andrew is an expert in these fields is somewhat of an understatement. I have had the privilege of working with Andrew as part of the what was originally the NERC Inverter-Based Resource Performance Task Force. It's now a subcommittee. But I thought I'd give you a little illustration of Andrew's impact on that group. I don't know how many of you are old enough to remember the old E.F. Hutton commercials from the 1980s, but if you weren't, E.F. Hutton was a stockbroker in the 1980s, and they had these commercials that they ran where it'd usually be a couple of guys, maybe in a public place, maybe like a restaurant or something like that. And at some point in the commercial, one of the guys would say, well, my stockbroker, E.F. Hutton says, and then everybody in the restaurant would stop and listen. And the punchline was something like, when E.F. Hutton talks, people listen. And that's kind of what I think about when Andrew speaks in a meeting. He's such an expert that when he talks, everybody stops what they're doing and they listen. So with that, I'm going to turn it over to Andrew in the room.
Check 1, 2. Thank you, Jeff, for very kind words. Appreciate it. I also just wanted to pause and say it's really nice to see your faces. Over the last 2 years, I know you've all had the same experience, but done a lot of so many Teams meetings and so many friends in the room here and so many people I've seen on Teams meetings so many times, and it's nice to see you in person. So really happy to be here. And thanks to Julia for inviting. Okay, so I want to start. I get to stand up here and talk and say, try and say smart things. But honestly, there's a lot of work that goes on behind the scenes with the studies that we do. And I just want to take a moment to acknowledge some of them. So Lucas Unruh, who's here, Anurada, we'll just say Anurada K for now. That's what we call him in the office. Serene, and engineers from Hawaiian Electric, Interconnection Services, Transmission Planning, System Operators, and other supporting divisions. So tons of study work has been done in this area, and they all have done a lot of work and really deserve credit. Also NREL and equipment OEMs really helped us a lot in the last couple of years in Hawaii. So I'm talking about Hawaii, as Jeff said, I'm a Canadian. So I'm going to borrow something from a mentor and a friend of mine who we lost over COVID named Mike Henderson. He used to start his presentations by saying anything he says that's correct and good, I'm going to attribute to Hawaiian Electric. I'm representing them. Anything that's wrong or somehow incorrect, that's my fault, not their fault. So we'll start that way by saying not necessarily a reflection of what Hawaiian Electric's position is. In fact, we have Lee Yu here as plant transmission planning manager from HECO. Okay, I'm going to start with now that I've said all sorts of nice things, I'm going to start with a reprimand for the industry. And this is, I'm mostly looking at the North American folks here, okay? So talking about Hawaii, they've got a number of these fragile islanded systems. By 2023, we're looking at 90% or maybe more penetration of inverter-based resources or converter-based resources. Leading the world, along with some of the folks we've heard today, we will later as well from Australia, in procuring and studying grid forming technology. So these folks have small islands. They're talking about building really relatively large GFM batteries and leaning on them to, in no sense, academic sense, preserve the stability of their system. So they need these big batteries to keep the lights on, period. And they need the grid forming technology. And so, they're trying to prevent blackouts. And so they're going to build these things for the first time, test them out on their actual system. And if they fail, they get blackouts. Okay. So the technology is for sale. We talked about this morning and I got a little bit grouchy about it. A very little marginal cost. Okay, and that's a fact. We've heard from several inverter manufacturers saying we don't care if you specify GFM or not. It's the same price. If there is a price from some, it's a marginal incremental cost. So the number of times I'm being asked to come and talk about Hawaii over the last 2 years and say, how is Hawaii doing with their grid forming? Look, go ahead and build it. Take a grid forming battery that's currently available and put it in your system and turn it on. Let's see what goes wrong. I don't know. We're going to probably have some problems with these things, but take one of your strong interconnections and do it. Okay, so that's my start off with a little bit of a gripe. Now let's go back to the content. So the drivers for the interconnection requirements in Hawaii, we're going to start with penetration levels, right? We've got very high renewable penetration levels. And we're talking now about not instantaneous where we hit this in sort of in an ordinary operating time frame, but N-0 before a fault, being 90%, close to 100%. Key is the second point, 50 to 70% of the generation at a normal time could be met by distributed energy resources. Okay, that's very high. That type of resource, as you know, is not subject to all of the standards we've been carefully developing for bulk grid. We don't need to do voltage control. We don't have to, we have very little visibility over that resource. And then finally, they're also worried about low fault current. So regular protection issues are kind of concerning to those guys. So the first one, you heard a very nice presentation from Deepak this morning. Thanks for presenting all of that detail, Deepak. This is really a steady state small signal that he referred to in the first presentations. In Hawaii, we studied everything in in detail, okay, as much detail as we could make, huge PSCAD models, and studied the scenario with no grid forming. It doesn't work, okay? This isn't a real surprise to anybody, but we showed it again in the Hawaiian system. You can't just do that. It won't be stable in a small signal sense, go unstable and is not viable. The second one is interesting, and we're learning more about it all the time with some of the more recent studies. This was identified in the first round of studies that Hawaiian Electric did, but now we're really shining a spotlight on it. And I'm going to use cartoons here. This is something I learned from our expert communicator, Nick Miller here, whose cartoons are the spice of life. And I love these types of cartoons because, they're drastic oversimplifications. I'm going to show you a lot more of them. We're going to forget about all the stuff that's real and just caricaturize everything. Okay, we're going to just really pretend all of that other stuff doesn't matter, just to drive home a point. So looking at this power out of the DER, what can happen, and we don't even really know for sure that this does happen. Okay, we have very little, hard data on what a really large distributed energy plant or system, let's say, looks like. But for now, let's say we have a good guess that when we go below a certain voltage during a fault, the active power is going to go to 0 because it'll block. Okay, it might be a fairly low block threshold, but more likely it might be a little bit higher. Goes to 0 power, then the fault comes back, the voltage comes back, and then you pause a little bit, maybe not very long, but you pause for a bit of time before you start to actively ramp up your active power. And then you ramp it back up, let's say over the next half a second, okay? So not a crazy, it's even some bulk grid stuff wants to do this. Let's say the DER does that. Now, if it's 70% of your energy mix, this is a pretty significant energy gap that we have here. And what we can see here in the bottom right is the frequency. It's really small, so I'll just say that the line at the top is a 60 hertz. The next line down is 59.5. Next line down is 50. And you can see that by the time we've got to 10.5 seconds, the frequency has hit 58.5 hertz, okay? And the initial fall of frequency, the rock off there, is really high. Okay, it's very fast. So we're talking about maybe 10 hertz per second. So now, what's going to happen because of this energy gap? The top plot you can see here is the megawatts of this is not megawatts of generation, but megawatts of load. Okay, what the Hawaiians are going to have to do to preserve that system is to start dumping load. If they get frequency that drops this low, their under frequency load shedding is going to start kicking. Okay, so we're going to lose a whole bunch of load. So not good. So what behavior do we want from grid forming? Now, again, these are caricatures and these are active power. We know that voltage is important. We're just going to ignore that. We know there's a lot of other stuff that happens here we're going to ignore. But for now, let's just look at the active power from these different types of technologies. So use a pointer instead of my finger. That might not be better. Okay, so top left-hand corner, if we have a grid following converter with no fast frequency response, we've seen a bunch of traces today that look kind of like this, but you're going to see the active power go to 0, probably come back up pretty quickly, bobble a little bit, and then stay more or less the same. Does that help us? Doesn't hurt us, but it's not really what we're looking for. We want to fill an energy gap that we're missing. So we're not going to do that by just holding the same power from the remaining resources. Second one, a grid following device with momentary cessation, a ramp rate, and no FFR. Well, that's even worse. We don't want that. Let's just throw that one out. Okay, synchronous condenser. Okay, now, oh, sorry, I'm mixing myself up here. We're going to mitigate the first problem first, okay, the small signal problem. The small signal problem being, the thing just starts to oscillate. We're not talking about the fault yet. sorry, next slide will be the energy gap. This one is a synchronous condenser. Now you can see this synchronous machine characteristic that we just saw in the previous presentation, a little oscillation. We don't have any new power, but we have this inertial type response here, okay? Now this is going to be helpful for us. This is resisting change in the system, and it's talking about all those things the National Grid folks were saying, where we're trying to add the stability back into the system. That's good. We want that. Synchronous machine with frequency response or active power control loops. In fact, this looks a lot like what we just saw in the slides from the previous presentation. That's good. Grid following with frequency response, still not good. We don't have the inertial response. The grid forming with frequency response, now we get this type of characteristic where we have the inertial response, but we decided, you know, we don't need to be exactly like a machine. Let's change the shape of this because we can, and just hold our power active. That's also good. We're still getting the inertial response. This might not look exactly like this, but that's also going to help us. Now, to mitigate that energy gap from the DER blocking that we were talking about, same kind of thing. We can throw out the grid following of no FFR. We don't get enough energy right here. Grid following with momentary cessation, no FFR, no good. Synchronous condenser, colored this yellow and put a question mark on it. Well, it's not hurting us. In fact, it is helping us a little bit. We get that energy, a little bit of that energy from the machine response, the inertial response. We have to be a little bit careful because this one is now going to swing. And, you know, it depends, right? We're going to have some energy here and then we have to give it back. So it might help us. Same with the synchronous machine with frequency response, or FFR, we'll call it, is good, but it's not necessarily what we want. We're really worried about this energy gap right here in this period where our momentary cessation is happening on the DER. Again, grid following with frequency response, not really going to help us, but this is perfect, right? That's exactly what we want for that application. We don't need much time here. You remember the momentary cessation or the DER might be back, as long as we can control the voltage and keep everything good in the system, might be back by a half a second. But we really like this characteristic. That's giving us all the energy that we can dump out of the battery or the supercapacitor or whatever we're talking about. And just for that period of time when we really need it. So this is a way to say, you know, well, in Hawaii, we have this problem of, you know, an energy gap from DER. This is the way, this is what we want your inverter to do. We don't necessarily even have to say exactly how you're going to do that control wise. We might give some suggestions, but really in our minds, this is what we're starting with. We really want to get that behavior. So how do you ask for this? And this is actually, honestly, the question of the year, probably for me and for a lot of you guys, and maybe will be for another year or two. How do we ask for grid forming in a way that makes the most sense, right? We don't want to cause more problems than we're solving. So this is not, I'm not going to say this is the way you should do it. This is the way we did it starting, you know, 2 years ago in Hawaii. We didn't really know exactly what control topologies were out there. We didn't know what manufacturers were going to be able to do. So we started with functional behavior. We said we wanted, in fact, we didn't even define the functional behavior. We just said, here's a model of some tests we're going to do. We're going to, for example, put your converter in a system, and we're going to drop a synchronous condenser from it, the last one. So now it's just you and the load. Is it going to be stable? That's the test. We're going to put your inverter together with another inverter of the same type. Are they going to fight? If not, that's a pass. Okay, if they fight, that's a problem. Is it going to get us frequency response that we want? And so we basically defined a set of tests that we're going to perform on the model that you give us. And that will be the pass or fail criteria for your technology and will be the sort of one of the gateways to interconnection. So that's what we're calling grid forming. Okay, so it's not really even a functional definition. It's just a set of tests that we're going to do on the system that's going to show you what you need to do. So that's one way to ask for grid forming. I'm not going to say that's going to work for everybody. In fact, I think the work, sort of the more theoretical work that everyone's doing right now is probably long-term going to be more useful, but this is where we went. Short presentation today. How can you confirm that this is going to work for you? How do you do the studies? And what's different about grid forming when you get into your studies? So that's tomorrow. You get to hear a presentation tomorrow about what to do there. I put a couple of links here for you. One is the modeling requirements we talked about. The other is just a 2020 grid forming study that was done for Hawaii with a lot of detail. And some of you have seen that presented over the last couple of years in various presentations, but I'm going to leave it there. So a grossly oversimplified presentation that represents really a lot of work from folks. So that's all.
All right, thanks, Andrew. Our final presentation today is from Deepak. And Deepak is a technical leader at EPRI. He's been there since 2017. When I first read that it was 2017, I was kind of surprised because it seems like as long as I have been following grid forming, inverter topics, Deepak's always been one of the thought leaders on that topic, and so happy to have him join us again. I guess he did the tutorial this morning, so happy to have him back. So Dr. Ramasubramanian, if I said that correctly, I'll turn it over to you.
Thanks, Jeff. You did say that correctly. It just rolls off the tongue, right? It's only 7 syllables long, nothing more. So what I'm going to be talking about today kind of, I think, evolves from what Tony, Dechao, and Andrew presented. We have this effort called the Unifi Consortium, which has kicked off from January this year. And this is some of the draft functional requirements that we have started talking about for grid forming as part of this Unifi Consortium. Please note that this is not final. We're going to keep tweaking this. We're going to keep changing this. We do want feedback from the industry at large, so which is why we're presenting here. And on the Unifi Consortium itself, Ben Kropowski will be talking more about it on Thursday. So I won't go into too many details about what exactly is the Unifi Consortium and what all does it constitute. I'll have a little bit of it here. And this presentation itself is combined work that we have done through Georgia Tech and EPRI in order to take this effort forward. So Unifi Consortium itself, just 2 slides to introduce it. It's a US Department of Energy funded effort for 5 years, co-led by NREL, University of Washington, and EPRI in a way to bring together various industry stakeholders across a wide spectrum of entities, right? So research labs, industry, equipment manufacturers, academia, and so on, to really push forth more grid forming technology into the system. And this is the kind of the team that we have at the moment in terms of who would be receiving funding and so on. And what we have as part of the work that we are doing is broadly into 3 different thrusts, both research and development and standardization and demonstration and commercialization. Again, as I said, Ben will be talking more about this on Thursday. So one of the things that we have been doing through this effort is trying to identify what do we want grid forming to be? How can we have it control agnostic? What are the types of functional requirements we want from them so that we can get more of these grid forming resources and the services that we want from them? And it is a little bit of an aspirational goal that we have in the next few slides. Some of it may seem a little bit of wishful thinking, but we are going towards wishful thinking in the hope that since we're going towards there, we'll at least get some of it, right? We do understand that there are caveats involved in terms of some of the specifications that we have listed. And that's where, as we talk towards with more inverter manufacturers, more system operators, and so on, we'll keep fine tuning it. But the goal at the end of the day is to have a broad set of performance specifications that we can use in terms of what we want to define as a grid forming inverter. A lot of text on the slide. I won't go through each of the details because I do realize we're also running up on time. But the way we are splitting this up, the way we are defining these functional requirements is to look at it from a broad picture of universally what we want. And then there are subset pictures in terms of what we want from a distribution perspective, if it's microgrid operation versus what we might want from a grid connected perspective in a distribution system environment itself. For example, if you have, let's say, a 1 megawatt plant connected in the distribution system, but it's grid connected, what you might want it to do, and then what might be specific requirements from a transmission system perspective. So one of the major things that we are looking at is the inverter shouldn't need to know what's happening outside in the world. In terms of, it shouldn't need to know whether there are synchronous machines connected or not. It shouldn't need to know whether there is a portion of the system islanded or not. It doesn't need to have explicit knowledge about the fact of whether it is grid connected or not. Irrespective of all those conditions, just using its local terminal information, just using what information it has available at its point of interconnection, it should work to support the grid. It should work to stabilize the grid. And whether this is in a grid following mode or grid forming mode may be a subset that we talk about later. But what we want the future inverter to do is, without getting that explicit communication from the system, it should work to support the grid. Now, what this might also mean is that we explicitly don't want to prescribe any mode switching. So there are certain resources, certain inverters from certain manufacturers which may look at switching modes. So they might operate in, say, a grid following mode and then switch to a grid forming mode if there is an islanding event that they detect, or if there is any other system operation that they detect. So what we want as an aspirational goal from the system side is we don't want that mode switching to occur. If it does occur, there should be no visible indication of it occurring on the grid side, because we don't want a change in mode to really impact the system. So it should be a seamless transition if at all it occurs, but the aspirational goal is that should not occur at all, which means that the way in which the grid forming inverter operates, both in the grid connected mode and in an isolated mode, should pretty much be the same in terms of the types of services that it provides. It should definitely droop based on frequency and voltage, because we don't want grid forming inverters to, like, if there's one grid forming inverter which doesn't have droop, by the nature of how it is created, the nature of how it is designed, it might try to take up the entire burden of a power system disturbance, because it would try to operate in maybe an isochronous mode and result in really it would try to control the frequency to the nominal value, right? So it should droop based upon both voltage and frequency, so that there is good power sharing across the different inverters in the system, good power sharing across the different resources in the system, both synchronous machines and inverter resources. We've spoken about damping and we've spoken about inertia, both from the tutorial that we had and from the kind of other presentations that we had. One of the things that we wanted to showcase is that the inverter should present a passive characteristic to the entire system. Now, this is more of a frequency domain criteria that we want to provide, or we want to get, that in terms of looking at the various frequencies across which the inverter controls operate, looking at the bandwidth of the inverter controls, it should essentially present a passive characteristic to the system so that you can go towards a more globalized stability criteria, which can be achieved with the grid forming inverters. It should be able to provide unbalanced current. It should be able to mitigate harmonics in the network. This may be a little bit more crucial for distribution system connected resources, especially if there are many single phase inverters present and you have a 3-phase grid forming inverter present. So the grid forming inverter in a way should act like an active device, which is going towards trying to mitigate the imbalance and mitigate harmonic injection in the system. Now, the next point is, of course, is a sticky point, right? We don't want the inverters to trip, except for internal faults. Now, we know that this is aspirational. We know that there are several limitations that might come about, especially when you go down to the equipment level, which might cause an inverter to trip. But what we want to aim for is to try to make the controls as robust as possible, that even if there is an energy constraint, even if there is a current limit constraint, even if there is some form of other control or saturation that occurs, the inverter should not trip and it should instead operate at that constraint. Now, again, this is a sticky point. We know that, and we want to further discuss this, and we want to further refine this as we go along. But many of the disturbances that we have observed in the system today have really caused a lot of inverter-based resources tripping for reasons that could have been potentially mitigated. One of the critical things that we want to ensure is using cyber-secure communications, because as you get more inverter-based resources, there's more of controls involved, there's more of communication network involved, there's less natural characteristics involved. So cybersecurity has to be integral into the development of the grid forming control, and for that matter, any inverter control that we think about. But since here we are talking about grid forming inverters, that's something that we want to really operate. Now, we spoke about droop, we spoke about sharing the power burden on the system, but at the same time, we also want these inverters to be dispatchable. So if you have a system operator planning what's going to be the next 1 hour dispatch, what's going to be the operational horizon for the next couple of hours, the system operator needs to be able to send commands to the various inverter-based resource plants and say that, okay, for the next 1 hour, we want you to operate at a certain P and Q level or a certain P and V level. So a grid forming inverter should also have the capability to be dispatchable in the near steady state requirement. We spoke about droop, we spoke about fault right through and low voltage requirements. One of the things about the microgrid operation that we wanted to look at is specifically have black start capability. Now, we may not require it for all grid forming inverters in the system, but we do want to start bringing in black start capability so that if the microgrid is islanded from the network and if there is a reason for it to go down, then it has the capability to be restarted and resynced back to the network. And the point which connects to that is being able to connect and disconnect with the system kind of at will. That is something which we will see as a uniqueness between distribution and transmission, where the aspirational goal is if there are inverters, at least in the distribution system, that keep disconnecting or connect back, they shouldn't cause a disturbance on the system, which means if the grid forming inverter is resynchronizing back to the grid after a trip, it should do so in a seamless manner. Some of the things that are specific for transmission system that we have identified is the need to provide negative sequence or zero sequence current faults, fault currents, which can be done in a variety of different ways, either as a proportionality factor or just actively try to control the sequence voltage to zero, which will just maintain a positive sequence voltage and then it will provide the negative sequence current. So because a lot of our existing protection needs that kind of a response. Now, we wouldn't, overhauling protection may be another topic that we want to think about, but at least to interface with existing protection mechanisms, we want the grid forming inverters. And this is something even for newer grid following inverters as per IEEE 2800, the ability to provide negative sequence control based upon the system. One thing that we spoke about in the tutorial was that grid forming inverters is not necessarily from the perspective of just a 100% IBR system. Especially when we look at the transmission network, there can be pockets of the system that are weak, which needs to be strengthened, which needs to be stabilized. So the grid forming inverter should have the capability to stabilize that system in that pocket or stabilize the weak network in that pocket. And we don't want it to introduce any new oscillatory modes. Now, there are some aspects here which we still don't know how we would test or how we would verify, because trying to not introducing new oscillatory modes is very much system dependent, is very much dependent upon the rest of the other devices that are present in the system and how they may interact with each other. So how we would exactly go about testing this out, we still don't know yet. That's what we'll keep working through the consortium. But we want to try to ensure that the newer inverters that are coming into the network will not introduce any newer oscillatory modes, and also seamlessly transition between daytime and nighttime operation. Now, this is something specific for solar plants, of course, but it can also be applied to any other inverter resource to seamlessly transition between non-zero megawatt injection and 0 megawatt injection or close to 0 megawatt injection. The reason for this is there have been certain events where a PV plant, as it starts ramping down towards the end of the day, starts witnessing certain oscillations because of the